Welcome to my video on Riemann sums. This is just a quick look at something that's called Riemann sums. It's named for this mathematician Riemann. And there's a couple things that I want you to be able to look at as you're going through here. The first is this definition. So we're going to say let f of x be defined on a closed interval a to b, and let P be a regular partition of A to B. And that's basically going to mean you're just going to subdivide it. We're going to let delta x be the width of each subinterval from x sub I minus 1 to x sub I. And for each I, let xi star be any point in that interval xi minus 1 to xi. Our Riemann sum is going to be defined for f of x as this. So the sigma from I equals 1 to n. So this is a big sigma notation, meaning we're just going to add things up, of f of xi star times delta x. Now, that definition is probably very confusing if you've never seen these before. So we're just going to kind of break it down real quick, and see what we get. So, and just bear with me, this is the first time kind of using this pen tool, so we're going to try it, see how it goes. All right, so first thing I'm going to do is I'm going to draw a nice straight number line here, and we're going to start over here on the left at A, and we're going to end over here on the right at B. And what we want to do, I'm going to lower that thickness just a little bit. What we want to do is subdivide this. So we're going to start making these regular intervals all the way from A to B, and it could be however many you get, 10, 5, 2, 18, 100, however many you want to make, that's the subdivisions. And usually what we'll do is we'll start here at x sub 0. That's going to be the same as A, and then we'll keep going down the list. So this is x1, x2, x3, all the way down till we get to this next to last one, x sub n minus 1, and then finally this b, which we'll also call x sub n. So those are what we're going to look at. So this is x sub 0, same thing as that a. Now, this width right here is going to be what we call delta x. So any particular width across these, they should all be the same for Riemann sums. So we're going to call that delta x. And delta x, you can see the formula right here. If you look at it, is going to be this b endpoint at b right there minus a, so the total length of the interval, divided by n, however many subdivisions you made. So that should make sense. It's the whole length divided by however many pieces you want to make. So that's going to be my delta x, just that width. And what we're going to multiply by is this function value at any x in this interval. So we're going to look at in a minute if they're a left point or a right point or a midpoint, but it really could be any point. Just left, right, or middle is usually an easy one to use. So we'll go ahead and take a look at those in just a second. But that function value at x sub I, that's going to represent a whole lot of different things. So one interpretation is with area. This will represent a height. Another one is, if you look at accumulation, this will represent a slope. So there's lots of different interpretations of this. When we get to some of the applications, your function might be the area of a disk or a washer. There's just lots of stuff that it could be. So keep in mind with these Riemann sums, this function here could be a height of a function, but it could also be a lot of other stuff that you're looking at that you want to add up that function value at each x in each of these intervals times this small little change in x. So that's kind of the idea. So we're just going to be adding up a bunch of these multiplications of function times small change. So if you go ahead and read through the paragraph here, you'll get kind of that idea that this function f of xi star, that's going to be the height of that rectangle. So we got the width is the delta x, we got the height is this function value, and we're going to go ahead and use that to define some areas. So if I go ahead and look at the bottom, I've got a few different areas here. So with this left one, we've got, looks like 10 subintervals. So this L10 means I'm doing a left-hand sum with 10 subintervals. And we've already kind of subdivided. So here's our subdivisions right across the x-axis right there. And we're just using the left side right there to get all the heights of these particular rectangles that are right there. So just whatever value is on the left of those intervals, we're just going to use that to make our height of that rectangle. And I'm going to go ahead and change this to something a little more noticeable and a little more thick. So all these left points we'll go ahead and just put in right here. And that'll make a left-hand sum. All right. So whatever those are times the width, basically taking all these areas. Now, notice if it's underneath, this is going to be a negative function value, so you'll actually get negative areas for all these parts under the curve, and positive, since the function height is positive, for all these that are above. So you can't have positive and negative areas that sort of cancel out to zero or become very small. That's just what's going to happen with us taking that height as the function value itself, possibly a negative function value. A right sum, same type of deal, but we're going to use the right point of these intervals. So everything on the right will go ahead and draw over. So this point's going to go over. This point on our curve is going to go over from the right of that interval across the whole interval. So this will make up all our rectangles. And you can tell, even though the curve is the same, the areas of these may or may not be the same. Midpoint, and kind of get the same idea on this one. We're just going to use the middle of this guy right here on all these different ones. So I won't fill all of them in, but this midpoint of all these intervals, so don't forget, this is my interval length, the midpoint right in the middle of that, that's going to be my function height. So whatever these function heights are times that width, we're just going to add up all these values and see what it gets. So this is what they call the area under the curve Riemann interpretation for Riemann sums. So this is going to be looking at negative area here, positive area up here, and just adding it all up and getting kind of an approximate value of that area. So I got some overestimate, some underestimate, might come out sort of close, but really you're just going to be getting an estimate on those guys for right now. So let's go ahead and do a quick example real quick right here. And this one I'm just going to be looking at, let's go and change this back down to 1 point. So this one I'm just going to be looking at approximating the area under this cubic, x cubed minus 4x squared plus 2x plus 3. We're going to be on the interval 0 to 3, and we're going to use a left-hand sum with 5 subdivisions. So I'm going to go ahead and we'll pause this real quick. All right, so what I'm going to try is right here at 0, we're going to start, and 3, we're going to end. And I want to use 5 subdivisions. So we want to break this up into 5 equal parts. So the first thing you'll usually do on these is you'll go ahead and compute out your delta x. So delta x is going to be my b minus a, so in this case 3 minus 0 over 5, and that's pretty easy to compute. That's just going to be 3/5. Just for the sake of kind of ease of computation, I'm going to go ahead and approximate that as 0.6. Actually, not an approximation, it's exact because it terminates, but we'll use the decimal 0.6 for the future of this one. So let's go ahead and draw in where those divisions are going to be. So we got a 0.6. This would be about 0.5. Going to be what, about right here, so a little bit past that. So there's the first subdivision at 0.6. The next one would be about 1.2, so probably about right there. The next one's going to be, let's see, 1.2 plus 0.6, so 1.8. That's going to be maybe right in here, probably pretty close to that intersection, maybe just a little bit past. The next one will be 2.4, so probably about there. And then finally we get to 3. So these are going to be all our values right there. We got 0.6, 1.2, 1.8, 2.4, and 3. And if you want to either write that on a graph or a table, whatever you like, sometimes that can help. And this one, all I'm going to do is just approximate these values. So left-hand sum, we'll go ahead and approximate that. And I'm going to make that just a little bit, well, we'll just go with it. So this is going to be my left-hand sum right here. Again, using this left value that's right there. Here, again, we're going to take that all the way over to the 1.2. Going to get another rectangle there. Follow at 1.2 this function value here over at 1.8. At 1.8, this might have maybe a slightly negative value right there, but say pretty close to 0. And then at 2.4, that function value is going to be right there. And follow that over till we get to 3. That'll be our last rectangle. And what we want to do is add the width times the height. So this is, just finding areas of all these rectangles, width times height, and we'll just add those up. So I'm going to go ahead and pause this, write it down just so it goes a little bit quicker right here. All right, so we have our sum from I equals 1 to 5 of our function times our delta x is going to equal this right here. So the 0.6, those are all my delta x's. It's all the same. The 3, that's my first function value. The next 3, the next one, the 1.5 right there. The negative 0.1 right there, and the negative 1.3 right there. And if you go ahead and calculate that out, so you can just put that in your calculator. This equals 3.66. So this is what we call the net area. So you have some positive area up here, some negative area up there, but positive minus that little bit down there gives you a total of this 3.66. Now, one way of computing this, if you don't want to write down all of these 0.6's, is you can factor that 0.6 out of there. So you could say 0.6 times this 3 plus 3 plus 1.5 plus or minus that 0.1 minus 1.3. So you can do that. That's one way of looking at it. It's kind of up to you. Sometimes that can save some time, particularly if there's a lot of, say, more than 5, maybe 10 of these. Just saves having to type in that 0.6 every time. So we're going to go ahead and say this left sum is 3.66. All right.